if I consider the second plane at half of it, what is OC? D0205, so 1/5. This is 1/10, then that next one is 1/5. So it should be somewhere there. I do it at 1/3. So this distance is about 0.33. So 1 by 3.333. So this goes somewhere there. So this becomes D030. So like that, if I have a plane which is suppose cutting it at 2 in mid, that is at 20 angstrom, 1 by D20 should be somewhere there. So what will be that value? No, so that cannot be there because that makes it a new plane of that. So it comes here. So all these reciprocal lattice points are going to fall on this axis, which are parallel. So now I am removing these parallel lines. Just as we keep 1 and the reciprocal lattice points which would come on that line. These are reciprocal lattice points corresponding to all the planes which are cutting B at different distances. Now I do it from 1. I was still now talking about planes which are parallel to A. So all the planes which are parallel to A are like this, right? At different distance from origin, but they are all parallel to OA. Now I am talking about set of planes which cut A at 1 and go like this. From here, the plane goes like that. From here, the plane can go like this. From here, the plane can go like that. Similarly, it can go and cut here at 1. So, what is the Miller indices? What would be the Miller index for this? 1. So, this becomes 1, 1, 0. If I do it like this, one, 2, 0, like this, 1/4 suppose. So 1/4, 1/3 would be somewhere there. Like that. So now the next thing that I am trying to do is to draw perpendicular from origin to all these planes. What is this distance? D110. I cut this point here at a distance 1 by D110 and mark this point as 110 reciprocal lattice point. Now I draw perpendicular from here to this. What is that distance? D120. I cut it at a distance 1 by D120 and it falls here. Mark this point as 120. And if we continue to do for all that, these points will come somewhere there and there, which will correspond to 130, 140 set of planes. Purposefully, I have drawn them in such a way that as if they are falling on one line. Now, I am only talking about the planes which are assumed to be parallel to my z. But who said it has to be parallel to z? These planes which are cutting here can be tilted such that it cuts z. So, the planes which I have drawn can have general Miller indices as 1, k, l. In this direction, k is changing, l remains fixed. If the plane is not like this but slightly tilted, the lines that are coming on the plane of the board will come slightly above the plane of the board in this row, will have same value of L, say 1, but it will be then 1, 1, 1, 1, 1, next one will be 1, 1, 2, 1, 1, 3, 1, 1, 4, 1, 1, 5 like that. Similarly here 1, 2, 0, 1, 2, 1, 1, 2, 2, 1, 2, 3 like that it will go, depending on how this plane is tilted. So in this direction, this plane you have a set of reciprocal lattice points. Here you have a set of reciprocal lattice points. Suppose from here to there, I say the distance is delta 1kl. So now for clarity and your better understanding, I am removing these in between things because those will create confusion. So what I am doing is I am just removing the drawing which are not required. Okay, I had already B, right? So suppose this is P and Q. What is this angle? Can be anything. Can be anything. I am saying it as phi. Instead of writing alpha, beta, gamma, which may be confusing that it is the interplanar angle. No, it can be anything. So phi. So now that point is M. So in this triangle, in case of triangle OAM, what is sine phi? What is sine phi? OM by OA. What is OM? What is OM? D1KL, right? And what is OA? Is A. So D1KL equal to A sin phi. Now we consider the triangle OPQ. What is this angle, Baba? This is phi, this is 90, this is 90 minus phi, sorry. See, I am also writing the wrong thing. That is why phi is better. 90 minus phi. So this becomes phi. So now what is sin phi here? Sin phi is PQ by OQ. What is PQ? Delta 1KL. What is OQ? 1 by D1KL. Which is equal to delta 1KL into D1KL. So that means from here what we get that D1KL is equal to sin phi by delta 1KL, right? Now we compare the two equations. D1K equal to A sin phi, and that is equal to sin phi by 1 by delta AK, delta 1KL. So we can equate these two as A sin phi equal to sin phi by delta 1KL. Sin phi is cancelled on either side. So delta 1KL is equal to 1 by A. Right? Any doubt? Delta is equal to delta 1KL equal to 1 by A. Now I will redraw those lines back. This is the 1KL line. I am drawing, 110 line. I am drawing 120 line. I am dropping a perpendicular from here and extending it to that point. So now, if I assume this angle is my phi, consider this blue triangle first. So my M comes here as M prime, Q goes there as Q prime, Q to P comes here as P prime. If this is phi, that angle is also phi. If I do the same set of mathematics using this triangle first, and then using that triangle and equate, we will end up getting delta 1KL as 1 by A once again. So that means all the reciprocal lattice points corresponding to those planes which cut A at one unit will fall on one line, and that line is at a distance delta 1 KL from the line which is here. Now if somebody can tell me this, then I don't need to derive. What is this plane? Cutting at half, that means 2, 2, 1, 0. In general terms, it is 2KL. K can be 1, 2, 3, 4. If K is 1, 2, 3, 4, the planes are like this, like that, and so on. And when the L is not 0, here L is 0 because it is parallel to Z. When L is not 0, that means it is cutting Z somewhere. So exactly the way it was doing, these are all like that. So for this particular plane, I am running out of colors. I drop a perpendicular from here to that plane and cut it at a distance here, which is 210 point. So the distance from here to there is delta 2KL what will be the value for delta 2KL? 2 by A, right? Everybody understood why 2 by A? Because this has become now A by 2. So whatever was here, A is becoming A by 2. So it becomes 2 by A. So in general, delta NKL equal to N by A. Right? So now, this is only along A. You do the same along B, you do the same along C, irrespective of the angle between A, B, C. Can be 90 degree, can be not 90 degree. What it generates is a set of points, set of imaginary points in space. Each and every point represents a plane in the direction S. And these points are called the reciprocal lattice points, which forms a reciprocal lattice, and the lattice constants are related to reciprocal lattice constants. So A, B, C and A star, B star, C star have inverse relationship. For cubic, tetragonal, orthorhombic, it is just 1 by A, 1 by B, 1 by C. For monoclinic and triclinic, the angle gets involved in it. But in all cases, all the planes that one can consider with respect to one origin in the unit cell is now converted to a three-dimensional grid of points. And those points are reciprocal lattice points which are required to understand the diffraction phenomenon. So in tomorrow's class, we will then see how these reciprocal lattice points help us in understanding the diffraction phenomenon. And from there we will define two types of spheres, sphere of reflection and Ewald sphere and all. So from there we will again continue how then you can design the data collection strategy based on the size of the Ewald sphere and all. Okay? So we stop here.